Okay, morning we discussed electrolysis, right? Electrolysis we discussed by using inert electrode and active electrode. Okay, first one, inert electrode. Since the nature of products obtained, okay, on nature of electrode we are using, whether we are using inert electrode or active electrode, and nature of products obtained also depends on what? Nature of electrolyte. Okay, whether we are taking electrolyte in aqueous state or molten state. Okay, second one, active electrode. And in this case, inert electrode, again we have two cases. One is molten state and another one is aqueous state. You may take molten electrolyte or aqueous electrolyte. If you do electrolysis of molten NaCl, for example, okay, Na plus cation moves towards cathode, anion moves towards anode, and they loses their charges. Okay, for example, if you have like this and electrolyte M plus X minus, M plus move towards cation, moves towards cathode, anion moves towards anode. Okay, and they lose their charges. M plus gives M, X minus, for example, if it is Cl minus, it gives what? Half Cl2 plus electron. X minus gives half X2 plus electron. Okay, right, that is molten state. And in the case of aqueous state, there is a competition between water and cations at cathode and water and anions at anode. Okay, if which cations are present, water undergoes reduction and lithium, sodium, potassium, calcium, magnesium, aluminum. If there is a competition between these cations and water, which one undergoes oxidation? Water undergoes oxidation. If water undergoes reduction, if water undergoes reduction, what is the product we will get? Hydrogen gas we will get. Hydrogen gas is evolved. This is at cathode. Water undergoes reduction. If there is a competition between these cations and water. Now at anode, if there is a competition between fluoride, nitrate, sulfate and water. If there is a competition between these anions and water, which one undergoes oxidation? Water undergoes oxidation. If water undergoes oxidation, what is the product we will get? Oxygen gas. If water undergoes oxidation, oxygen gas is evolved. Next one, active electrode. Active electrode, okay, we discussed electrolysis by using copper electrodes, electrolysis of copper sulfate by using copper electrodes, or electrolysis of silver nitrate by using silver electrodes. If you do electrolysis of copper sulfate using copper electrodes, what happens? At anode, copper goes into the solution as copper 2 plus ions. At cathode, those copper 2 plus will be deposited. So net change is nothing but simply copper migrates from anode to cathode. In the case of silver nitrate also same. Ag goes into the solution as Ag plus ions at anode. That Ag plus ions will be deposited at cathode. So silver migrates from anode to cathode. And this phenomena is useful in electroplating and electro refining of metals. This phenomena is useful in electroplating and electro refining of metals. So this is electrolysis. Okay, these concepts you have to remember from electrolysis. Next we discussed electrolysis of water. For electrolysis of 1 mole of water, how many Faradays are required? For 1 mole of water, 2 Faradays are required. Okay. If you do electrolysis of 1 mole of water, what are the products we will get? H2 plus of O2. How many Faradays are required? 2 Faradays are required for electrolysis of 1 mole of water. The number of moles of H2 and O2 obtained are 1:1/2 or 2:1. Volume of H2 and O2 obtained also same. Volume is directly proportional to number of moles. So 1:1/2 or 2:1. Next, weight of H2 and O2 obtained is 2 grams. This is what? 8 grams. Half O2 means 8 grams. Okay na? Antena? 32 by 2, 16 grams. 2 is to 16 and 1 is to 8. Weight of H2 and O2 obtained ratio if you take 1 is to 8 and 2 is to 16. So we get 1 is to 8. Okay. Up to that we discussed. Next one and concept of Faraday. What is Faraday? Faraday is nothing but it is the charge carried by 1 mole of electrons, right? It is the charge carried by 1 mole of electrons. It is the charge carried by 1 mole of electrons. Okay. So 1 mole of electrons means how many moles of electrons we have to take? So 1 Faraday means equal to how many moles of electrons? Avogadro number of electrons, that is 6.02 into 10 power 23 number of electrons we have to take. What is the charge carried by an electron? 1.602 into 10 power minus 19 coulombs, right? The charge carried by an electron is 1.602 into 10 power minus 19 coulombs only. As we are calculating for 1 mole of electrons, okay, in some books it is given per mole also, okay, as we are calculating for 1 mole of electrons, charge carried by 1 mole of electron. So if you simplify this, nearly how much will get? 96,500 coulombs will get it. So 96,500 coulombs is called what? 1 Faraday. So charge carried by 1 mole of electrons is nothing but 96,500 coulombs, which is called as 1 Faraday. Okay. Next one, for example, I am taking monovalent or univalent cations. I am taking it. Monovalent cations or univalent cations, for example, sodium plus, potassium plus, lithium plus, etc. I am taking monovalent cations, or in general I am indicating M plus only. Okay, to deposit 1 mole of univalent cation on electrode, how many moles of electrons are required? To deposit 1 mole of univalent cation, how many moles of electrons are required? 1 mole of electrons are required. If you take Na plus electron gives rise to Na. So to deposit 1 mole of univalent cations, how many moles of electrons are required? 1 mole of electrons. 1 mole of electrons means how many Faradays are required? 1 Faraday is required. Okay. So to deposit 1 mole of univalent cations, how many Faradays are required? 1 Faraday is required. To deposit 1 mole of univalent cations, 1 Faraday is required. Okay. Now let us consider we want to deposit 1 mole of bivalent cation. I want to deposit 1 mole of bivalent cation. For example, M2 plus, for example, calcium 2 plus, magnesium 2 plus, okay, etc. To deposit 1 mole of bivalent cation, how many moles of electrons are required? 2 moles of electrons are required. To neutralize 2 units of positive charge, how many moles of electrons are required? 2 moles of electrons are required. That means to deposit 1 mole of bivalent cations, how many Faradays is required? 2 moles of electrons means charge carried by 2 moles of electrons is 2 Faradays only. Write that point. To deposit 2 moles of bivalent cations, 2 Faradays is required. To deposit 1 mole of bivalent cations, how many Faradays are required? 2 Faradays are required. 2 Faradays are required. Similarly, if you want to deposit 1 mole of trivalent cations, for example, Al3 plus and Fe3 plus, to deposit 1 mole of trivalent cations, how many Faradays are required? 3 Faradays are required. To deposit 1 mole of trivalent cations, 3 Faradays are required. Since how many moles of electrons are required? 3 moles of electrons. Al 3 plus 3 electrons gives rise to Al. Al 3 plus 3 electrons gives rise to Al. So to deposit 1 mole of trivalent cations, 3 Faradays are required. Okay, and now I am asking like this only. By passing 1 Faraday of electric current, how many moles of univalent cations are deposited? By passing 1 Faraday of electric current, how many moles of univalent cations are deposited? 1 mole of univalent cations are deposited. 1 mole of univalent cations are deposited. Now tell me, by passing 1 Faraday of electric current, how many moles of bivalent cations are deposited? Okay, by passing 1 Faraday of electric current, how many moles of bivalent cations are deposited? Half mole. How many Faradays are required for 1 mole? 2 Faradays are required for 1 mole. So if you pass 1 Faraday, how many moles of bivalent cations are deposited? Half mole of bivalent cations are deposited. So half mole of bivalent cations are deposited. Half mole of bivalent cations are deposited by passing 1 Faraday of electric current. Now tell me, if you pass 1 Faraday of electric current, in our solution trivalent cations are there. How many moles of trivalent cations are deposited? 1 by 3. 1 by 3 moles of trivalent cations are deposited. Since to deposit 1 mole of trivalent cations, how many Faradays are required? 3 Faradays. So if you pass 1 Faraday, how many moles of trivalent cations are deposited? 1 by 3 moles. Okay. If valency is n, if you pass 1 Faraday of electric current, 1 by n moles of cations will be deposited. Okay. So now tell me, by passing 1 Faraday of electric current, how many gram equivalents of univalent cations are deposited? By passing 1 Faraday of electric current, what is the number of gram equivalents of univalent cations deposited? What is the relation between number of gram equivalents and number of moles? Number of gram equivalents is equal to number of moles into n factor. Number of gram equivalents is equal to number of moles into n factor. For ions, n factor is nothing but valency. For ions, n factor is nothing but valency. For univalent cations, valency is 1. So number of gram equivalents and number of moles both are same. So if you pass 1 Faraday of electric current, how many gram equivalents of univalent cations will be deposited? 1 gram equivalent. Since 1 mole we have, if you substitute 1 into 1, n factor is 1 for univalent cations. So 1 gram equivalent of univalent cations are deposited. 1 gram equivalent of univalent cations are deposited. Now if you pass 1 Faraday of electric current, how many gram equivalents of bivalent cations are deposited? How many gram equivalents of bivalent cations are deposited? Okay, Randy. In this case, number of gram equivalents is equal to 1 into 1, 1. Here, number of gram equivalents is equal to, if you pass 1 Faraday of electric current, how many moles of bivalent cations are deposited? Half mole. What is n factor for bivalent cations? 2. That means how many gram equivalents will be deposited? 1 gram equivalent. Again, for bivalent cations also, how many gram equivalents will be deposited? 1 gram equivalent. So 1 gram equivalent of bivalent cations are deposited. So number of gram equivalents of bivalent cations deposited also 1. Now if you pass 1 Faraday of electric current, how many gram equivalents of trivalent cation will be deposited? Again 1 only. So number of gram equivalents is equal to how many moles of trivalent cations are deposited? 1 by 3. What is n factor for trivalent cations? 3. So therefore again how many gram equivalents? 1 gram equivalent of trivalent cations deposited. That means by passing 1 Faraday of electric current, always how much amount of substance will be deposited? 1 gram equivalent of substance will be deposited. That is the conclusion, just you remember that. Okay. Right, to deposit 1 mole of univalent cations, 1 mole of electrons are required. That means 1 Faraday is required. To deposit 1 mole of bivalent cations, 2 moles of electrons are required, that means 2 Faradays. Similarly, for 1 mole of trivalent cations, 3 Faradays are required. Or if you pass 1 Faraday of electric current, how many moles of univalent cations deposited? 1 mole. If for 1 Faraday, how many moles of bivalent cations deposited? 1 by 2. For 1 Faraday, the number of moles of trivalent cations deposited is 1 by 3. 1 mole of univalent cations means how many gram equivalents? 1. Half mole of bivalent cations means how many gram equivalents? 1 only. 1 by 3 moles of trivalent cations means 1 gram equivalent. So that means by passing 1 Faraday of electric current, always 1 gram equivalent of substance will be deposited. Write that point. Therefore, by passing 1 Farad of electric current, therefore, by passing 1 Farad of electric current, therefore, by passing 1 Farad of electric current, by passing 1 Farad of electric current, always 1 gram equivalent of substance, always 1 gram equivalent of substance will be deposited. Therefore, by passing 1 Farad of electric current, always 1 gram equivalent of substance will be deposited. Now, 1 gram equivalent of substance deposited means what is the weight of substance deposited? What is the weight of substance deposited? Molecular weight. Number of gram equivalents is equal to what is the formula? Weight by equivalent weight in grams, gram equivalent weight. Number of moles means weight by gram molecular weight. Number of gram equivalents means weight by equivalent weight. How many gram equivalents of substance will be deposited? And by passing 1 Faraday, 1 gram equivalent. So 1 is equal to weight by equivalent weight. So the weight of substance deposited is nothing but what? It's a equivalent weight. So if you pass 1 Faraday of electric current, the number of gram equivalents of substance deposited is 1. 1 is equal to weight by equivalent weight. Then weight of substance deposited is equal to what? Its equivalent weight. Right? Therefore, by passing 1 Faraday of electric current, therefore by passing 1 Farad of electric current, the weight of substance deposited, is equal to, by passing 1 Farad of electric current, the weight of substance deposited is equal to its equivalent weight, For example, we are passing 1 Farad of electric current and then what is the weight of Ag plus ions deposited? And what about weight of silver deposited? In the solution Ag plus ions we have Ag plus is deposited as Ag. What is the weight of silver deposited? Weight of silver deposited is nothing but what? Equivalent weight. Equivalent weight is given by what? How to get equivalent weight? And equivalent weight is atomic weight or molecular weight by n factor. Atomic weight or molecular weight by n factor. So what is the atomic weight of silver? And 107.8 or nearly 108, right? By what about n factor for silver? 1. So therefore weight of silver deposited is what? 107.8 grams. Nearly 108 grams of silver will be deposited if you pass 1 Farad of electric current. If you pass 1 Farad of electric current through a solution having copper 2 plus ions, we are passing 1 Farad of electric current through a solution having copper 2 plus ions. What is the weight of copper deposited? The weight of copper deposited is nothing but its equivalent weight. What is equivalent weight of copper? What is copper atomic weight? 63.5 by n factor. N factor for copper is 2, valence is 2, copper 2 plus valence is 2, so that means we get 31.75 grams. So if you pass 1 Farad of electric current through a solution containing copper 2 plus ions, what is the weight of copper deposited? 31.75 grams of copper will be deposited. If you pass through a solution having Al3 plus ions, What is the weight of aluminum deposited? 27 by 3, right? That is 9 grams of aluminum will be deposited. So like this we can calculate. If you pass 2 Faradays, what is the weight of aluminum deposited? 18 grams. Okay. If you pass 1 Faraday of electric current, 9 grams of aluminum will be deposited. If you pass 2 Faradays, 18 grams of aluminum will be deposited, and so on. Okay, so by passing 1 Faraday, the weight of substance deposited is nothing but its equivalent weight. And next point, right? By passing 1 Faraday of electric current, 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 comma, the volume of gas evolved, the volume of gas evolved, the volume of gas evolved is called equivalent volume, is called equivalent volume. For example, I am indicating as VE and equivalent volume. The weight of substance deposited is nothing but equivalent weight. The volume of gas evolved is nothing but equivalent volume. Okay, for gases we can write equivalent volume. For example, if you pass 1 Farad of electric current through a solution having H plus ions, H plus ion is deposited as what? H2 gas. So H2 gas is evolved. So what is the volume of H2 gas evolved? Okay, for example, oxygen gas is evolving at electrode. What is the volume of O2 gas evolved? Okay, if you see that, equivalent volume of hydrogen gas. Okay, that we discussed in various methods to express concentration. At that also we discussed equivalent volume of hydrogen, nitrogen, oxygen gases we discussed. Okay, once again I am explaining here. What is the equivalent weight of hydrogen? And equivalent weight of hydrogen. Equivalent weight of hydrogen is how much? 1 gram. Equivalent weight of hydrogen is 1 gram. So if you pass 1 Farad of electric current, if you pass 1 Farad of electric current, what is the weight of hydrogen deposited? And 1 Farad of electric current, if you pass, weight of hydrogen deposited is 1 gram. Weight of hydrogen deposited is 1 gram. The weight of hydrogen deposited is nothing but its equivalent weight. Equivalent weight of hydrogen is 1 by 1, 1 only. And now, what is the number of moles of hydrogen gas evolved? And what is the number of moles of hydrogen gas evolved? Okay, weight of hydrogen gas evolved is hydrogen. Okay, 1 gram of hydrogen deposited as H2 gas. And 1 gram of hydrogen deposits as H2 gas. So what is the weight of H2 gas evolved? 1 gram. Okay, then. Okay, and now number of moles is equal to weight by molecular weight. What is the molecular weight of H2? 2. So how many moles of H2 gas is evolved? Half mole of H2 gas is evolved. So number of moles of H2 gas evolved is half mole. That means what about equivalent volume? And under STP conditions, if you take 1 mole of any gas under STP conditions occupies how much volume? 22.4 liters. That means equivalent volume of H2 will get 11.2 liters. This is under STP or NTP conditions. Okay, and if you pass 1 Farad of electric current, the weight of hydrogen deposited is 1 gram. That 1 gram of hydrogen deposits as H2 gas. So the number of moles of H2 gas obtained is weight by molecular weight, that is 1 by 2. Half mole of H2 gas is evolved. Half mole means how many liters? 11.2 liters. So what is the equivalent volume of hydrogen gas? 11.2 liters under STP conditions. Similarly, if you take for equivalent volume of oxygen gas, if you pass 1 Farad of electric current, how many liters of oxygen gas will be evolved? If you pass 1 Farad of electric current, how many liters of oxygen gas will be evolved? What is the equivalent weight of oxygen? What is the equivalent weight of oxygen? 8 grams. 16 by 2. Atomic weight by N factor. What is N factor for oxygen? 2. 16 by 2. That is 8 grams. Equivalent weight of oxygen is 8 grams. That means number of moles of O2 obtained is 8 by weight by molecular weight. What is the molecular weight of O2 gas? 32. That means how many moles of O2 gas evolved? 1 by 4 moles of O2 gas will be evolved if you pass 1 Faraday of electric current. Okay, this is for 1 Faraday of electric current. If you pass 1 Farad of electric current, number of moles of O2 gas evolved is 1 by 4 moles. That means what about equivalent volume under STP conditions? 1 by 4 into 22.4. That means we get 5.6 liters. So 5.6 liters of O2 gas is evolved under STP conditions if you pass 1 Farad of electric current. So mostly we may get hydrogen gas, oxygen gas and chlorine gas. So these three you may remember. Chlorine gas. Okay, what is the equivalent weight of chlorine? Equivalent weight of chlorine, atomic weight is 35.5 by what about valency on chlorine? 1. So that is 35.5 grams. So what about the number of moles of chlorine gas evolved? Number of moles is equal to weight by molecular weight. 35.5 by what about the molecular weight of chlorine? Cl2 gas. That is 35.5 plus 35.5. That is 71. 71. So the number of moles of chlorine gas evolved is 1 by 2. So what about equivalent volume of chlorine under STP conditions? 1 by 2 into 22.4. That means equivalent volume of chlorine is also 11.2 liters. Okay, Nandi. So if you pass 1 Farad of electric current, weight of substance deposited is equal to equivalent weight. Volume of substance deposited is equal to equivalent volume. Okay, weight of substance deposited is equal to equivalent weight. Volume of gas evolved is equal to equivalent volume. If you see equivalent volume for H2 and Cl2 same, that is 11.2 liters, whereas equivalent volume for oxygen gas is 5.6 liters. Okay, this you may remember. If you pass 1 Farad of electric current, the weight of substance deposited is nothing but its equivalent weight. The volume of gas evolved is nothing but its equivalent volume. Equivalent volume under STP conditions for hydrogen and chlorine gases are 11.2 and for oxygen gas it is 5.6 liters. So equivalent weight is nothing but atomic weight or molecular weight by n factor. Okay. This is the concept of Faraday. And next one, Faraday's laws of electrolysis we have. Faraday's laws of electrolysis. How many laws we have? 2 laws we have. 2 Faraday's laws we have. Faraday first law and Faraday second law. Faraday's laws of electrolysis. In that first put heading Faraday's first law. Faraday's first law. Faraday's first law. So according to Faraday's first law, okay, for example, if you pass 1 Farad of electric current, okay, on passing 1 Farad of electric current, what about the weight of aluminum deposited? Weight of aluminum deposited is nothing but its equivalent weight. What is the equivalent weight of aluminum? 27 by 3, 9 grams. If you pass 2 Faradays of electric current, what about the weight of aluminum deposited? 18 grams. If you pass 3 Faradays, the weight of aluminum deposited is equal to 27 grams. So that is nothing but Faraday's first law. So Faraday's first law is nothing but the weight of substance deposited at an electrode during electrolysis is directly proportional to what? Quantity of electric current we are passing. If you pass more quantity of electric current, more amount of substance will be deposited. If you pass more amount of electric current, more amount of substance will be deposited. Okay. For example, if you pass 1 farad of electric current, what is the volume of oxygen gas evolved? 5.6 liters. If you pass 2 farad of electric current, what is the volume of oxygen gas evolved? 11.2 liters. Okay, so the weight of substance deposited or the volume of gases evolved during electrolysis at an electrode is directly proportional to quantity of current we are passing. Okay, that is Faraday's first law. Write the statement. Any problem? Right. The weight of substance deposited, the weight of substance deposited, the weight of substance deposited at an electrode, the weight of substance deposited at an electrode during electrolysis, the weight of substance deposited at an electrode during electrolysis is directly proportional to quantity of electric current passed through the solution, is directly proportional to the quantity of electric current passed through the solution. That is, W is directly proportional to Q, where Q is the quantity of current, in coulombs, W is directly proportional to Q, where Q is the quantity of current in coulombs. So W1 by W2 is equal to, we get Q1 by Q2 only. Okay. Or it may be written like this also. W is directly proportional to AT and AT, where Q is nothing but A into T. Okay. 1 coulomb is nothing but 1 ampere second and 1 ampere second. Okay, coulomb may be written as ampere into time. So 1 coulomb is nothing but that is the quantity of current passed in amperes per 1 second. Okay, coulomb is nothing but what? Quantity of current passed in amperes per 1 second. If you take T is equal to 1 second, then quantity of current passed in amperes is called what? Quantity of current in coulombs. Okay, so 1 coulomb is equal to 1 ampere second. We can write like that also. Next one, if you remove the proportionality, we will get a constant. If you remove the proportionality, we will get a constant. Okay, that I am indicating with Z. Z is called as electrochemical equivalent. Z is called as electrochemical equivalent. Z is called as electrochemical equivalent. How can you define Z if you see? So Z is nothing but what here? W by Q. Z is nothing but W by Q. If Q is equal to 1 coulomb, quantity of current passed is 1 coulomb. If quantity of current passed is 1 coulomb, then what about the weight of substance deposited? Weight of substance deposited is nothing but what? Z. If Q is equal to 1, the weight of substance deposited is equal to Z. So how can you define Z? Z is nothing but it is the weight of substance deposited by passing 1 coulomb of electric current. If you pass 1 coulomb of electric current, what is the weight of substance deposited? That is called as Z, electrochemical equivalent. So electrochemical equivalent defined like this only. It is the weight of substance deposited. It is the weight of substance deposited. It is the weight of substance deposited. It is the weight of substance deposited by passing. It is the weight of substance deposited by passing 1 farad of electric current. Sorry, 1 coulomb of electric current. It is the weight of substance deposited by passing 1 coulomb of electric current. by passing 1 coulomb of electric current. Okay, if you see Z value for aluminum, what is Z value for aluminum? If you pass 96,500 coulombs of electric current, what is the weight of aluminum deposited? If you pass 96,500 coulombs means 1 farad of electric current, what is the weight of aluminum deposited? 9 grams. Now we have to calculate for 1 coulomb. If you pass 1 coulomb, what is the weight of aluminum deposited? What we get in? For 96,500 coulombs, 9 grams is deposited. For 1 coulomb, how many grams will be deposited? That is 9 by 96,500 grams of aluminum will be deposited. This is called as what? Z. The weight of substance deposited is called as Z, electrochemical equivalent. So, what is the Z value for aluminum? 9 by 96,500. That is the Z value for aluminum. What is the Z value for copper? What is the Z value for copper? If you pass 96,500 coulombs, what is the weight of copper deposited? 31.75 grams. Now, what about for 1 coulomb? So, weight of copper deposited is nothing but Z, that is 31.75 by 96,500 coulombs. What is electrochemical equivalent for silver? Directly I am writing. What we get? 107.8 by 96,500 grams. That is the weight of silver deposited if you pass 1 coulomb of electric current. For 96,500 coulombs, 108 grams of silver will be deposited. Then what about for 1 coulomb? 108, nearly 108 by 96,500 grams of silver will be deposited. So, whether Z value is same for all substances or Z value is different for different substances. Z value is different for different substances. So, Z is said to be a characteristic of a given substance. Z value depends on nature of substance. Write that point. Z value depends on nature of substance. Z value depends on nature of substance. Z value depends on nature of substance. Next, it is characteristic of a given substance. It is characteristic of a given substance. Z value depends on nature of substance, or it is characteristic of a given substance. Okay. Right, and this is Faraday's first law. Weight of substance deposited is directly proportional to quantity of current we are passing in coulombs. W1 by W2 is equal to what we get? Q1 by Q2. If you remove the proportionality, we will get Z. Okay, Z is defined like this. If you pass 1 coulomb of electric current, the weight of substance deposited is called Z. That is different for different substances. So, it depends on nature of substance, or it is characteristic of a given substance. Next one, put a note. For example, if you pass 1 farad of electric current, 1 farad of electric current or 96,500 coulombs of electric current, the weight of substance deposited is nothing but what? It's a equivalent weight. Equivalent weight I am indicating as E. If you pass 1 farad of electric current or 96,500 coulombs of electric current, the weight of substance deposited is equivalent weight. Then if you pass Q coulombs of electric current, what is the weight of substance deposited? What is the weight of substance deposited? That we can calculate as W is equal to Q by F into E. Q by F into E. Or QE by F and QE by F. Or Q may be written as A into T. So, EAT by F and E. If Q is given and they ask you to calculate what is the weight of substance deposited, we can calculate like this one, QE by F. For example, on passing, let us consider on passing 965 coulombs of electric current, what is the weight of aluminum deposited? I am asking like this one. On passing 965 coulombs of electric current, what is the weight of aluminum deposited? How to calculate it? So weight of aluminum deposited is equal to QE by F. What is Q? How many coulombs of electric current we are passing? 965. E. What is the equivalent weight of aluminum? 9. F. 96,500. So 100 times gets cancelled. So we get 0.09 grams. So that is the weight of aluminum deposited. Or we can follow like this also. W1 by W2 is equal to Q1 by Q2. If you apply here 96,500, what is the weight of aluminum deposit? 9. Okay, weight of aluminum deposit we want to calculate. Q1 96,500 and we want to calculate for 965 coulombs, 100. So W is equal to 9 by 100. So we get 0.09 grams. So you may follow either like this or like this. W is equal to QE by F, or W1 by W2 is equal to Q1 by Q2. Okay, Q1 I am taking 1 Faraday, 96,500 coulombs. Then weight of aluminum deposited is 9 grams. Then for 965 coulombs, what is the weight of aluminum deposited? Okay. Let us consider I am giving like this. On passing 965 amperes of current, on passing 965 amperes of current, for 10 seconds, what is the weight of aluminum deposited? On passing 965 amperes of current for 10 seconds, what is the weight of aluminum deposited? What is the formula? W is equal to EAT by F. What is the equivalent weight of aluminum? 9 grams. We are passing 965 amperes. For how many seconds? 10 seconds. F value is 96,500. So 10 times gets cancelled. That means 0.9 grams. So the weight of aluminum deposit is 0.9 grams. Otherwise you can follow like this also. W1 by W2 is equal to Q1 by Q2. Okay, Q1 I am taking 96,500. If you take Q1 96,500 coulombs, what is the weight of aluminum deposited? 9. So W2 we want to calculate. Q2 is nothing but what? A into T. Q is nothing but what? A into T. So Q2 is nothing but A into T. What we get? 965 into 10, 9,650. So 10 times gets cancelled. So W is equal to 9 by 10. Get 0.9 grams. Okay. This is for weight, and if you volume is given. Next one, Andy. If you pass 1 Faraday of electric current, that is 96,500 coulombs, the volume of gas evolved is nothing but what? Its equivalent volume. If you pass 1 Faraday of electric current, the volume of gas evolved is nothing but its equivalent volume. Then if you pass Q coulombs of electric current, what is the volume of gas evolved? So what we get? V is equal to Q by F into VE. Okay, Q into VE by F. See the difference, Andy. Here we are taking weights, Andy. Okay, if you take weight, here we get equivalent weight. If you take here volume, here we get equivalent volume. Right? Previously we got VE. This is E and EAT by F. Now VEAT by F. Just to see the difference, and if you take weight of substance, we have to substitute what? Equivalent weight. If you take volume of gas evolved, we have to substitute equivalent volume. Right? For example, I am asking question like this. On passing 96.5 coulombs of electric current, on passing 96.5 coulombs of current, what is the volume of H2 gas evolved under STP conditions. On passing 96.5 coulombs of electric current, what is the volume of H2 gas evolved under STP conditions? V is equal to Q. How many coulombs we are applying? Q into V by F, 96.5 coulombs. What is equivalent volume of H2 gas? 11.2 liters. F means 96,500. So, what will get? And how many times gets cancelled? 1000 times. Huh? So, therefore, V is equal to 11.2 into 10 power minus 3 liters. 0.0112 liters of hydrogen gas is evolved, or in ml if you convert, 1 liter is equal to 1000 ml. So, 11.2 ml, 11.2 ml of H2 gas is evolved. Or you may follow like this also. V1 by V2 is equal to Q1 by Q2. V1 by V2 is equal to Q1 by Q2. One we have to take 96,500. If you take 96,500, here we will get 11.2. Next one given 96.5. 96.5 means how many times gets cancelled? 1000 times. So, V2 is equal to what? And 11.2 into, if you bring this 1000 left side, it is 10 power minus 3 liters, or 11.2 ml. So, 11.2 milliliters of hydrogen gas is evolved if you pass 96.5 coulombs of electric current through a solution having H plus ions. Okay. So, next one, for example, I am giving like this: on passing 965 amperes of current, on passing 965 amperes of current for 100 seconds, on passing 965 amperes of current for 100 seconds, what is the volume of O2 gas evolved? What is the volume of O2 gas evolved under STP conditions? On passing 965 amperes of current for 100 seconds, what is the volume of O2 gas evolved? V is equal to what? Q into VE by F. Q can be written as AT, VE AT by F. VE AT by F. VE, what is equivalent volume on it? For O2 it is 5.6 liters under STP conditions. A given 965, time given 100 seconds, by 1 Faraday means 96,500, gets cancelled. So, volume of O2 gas evolved is nothing but 5.6 liters. Otherwise, if you do Q is equal to A into T, we are getting 96,500 coulombs. If you pass 96,500 coulombs, volume of gas evolved is nothing but its equivalent volume, that is 5.6 liters will get directly. Okay, right? Or you can follow like this also: Q1 by Q2 is equal to V1 by V2. Okay, or directly also we can think on Q is equal to A into T. So, 965 into 100, 96,500. 96,500 coulombs means the volume of gas evolved is equivalent volume, that is 5.6 liters. Okay. This is Faraday first law. Next one, Faraday's second law. Faraday's second law. Okay, Faraday second law. Faraday's second law. Okay, according to Faraday's second law, we are taking 3 electrolyte solutions or 2 electrolyte solutions, 2 or 3 electrolyte solutions we are taking. They are connected in series and they are connected in series. Same quantity of electric current we are passing all through all these electrolyte solutions. Same quantity of electric current we are passing through all these electrolyte solutions. Then the ratio of weights of substance deposited. Then the ratio of weights of substance deposited is in the ratio of their equivalent weights. Okay, here the ratio of substance deposited, W1 is to W2 is to W3 is nothing but what? E1 is to E2 is to E3 and if you take gases and the ratio of volumes of gases evolved is nothing but in the ratio of their equivalent volumes and VE1, VE2 is to VE3. Okay, the ratio of volume of gases evolved is in the ratio of their equivalent volumes and okay, first write the statement, I will explain by an example. Okay, Faraday's second law, right? When same quantity of electric current is passed through different electrolyte solutions, connected in series, then the ratio of weights of substances, deposited, at electrodes, then the ratio of weights of substance deposited at electrodes is in the ratio of their equivalent weights. Then the ratio of weights of substance deposited at electrodes is in the ratio of their equivalent weights. Okay, for example, here we are taking 3 electrolyte solutions, same quantity we are passing. So W1 is to W2 is to W3 is equal to what? E1 is to E2 is to E3. Our volume of gases evolved is VE1 is to VE2 is to VE3. Okay, the ratio of volumes if you take, what will get? If you take volumes, here we will get what? Equivalent volumes. Okay, in that case the ratio of volume of substance evolved in the place of deposited we may say evolved. The ratio of volume of gases evolved at electrodes is in the ratio of their equivalent volumes. I will explain by an example. For example, we are passing same quantity of electric current through silver nitrate solution and copper sulfate solution. Let us consider through silver nitrate solution and copper sulfate solution. If you see the weight of, for example, we are passing 1 farad of electric current through both the solutions. What about the weight of silver deposited? It is nothing but its equivalent weight for 1 farad, that is 107.8 grams. What about the weight of copper deposited? 31.75 grams. Now if you pass 2 farads of electric current, what is the weight of silver deposited? 2 into 107.8 grams. Here 2 into 31.75 grams. So if you see here, what about the ratio of weights of silver and copper deposited? That is nothing but 107.8 is to 31.75. What about here? The ratio of weights of silver and copper deposited. The ratio of weights of silver and copper deposited is again same we will get or not? 2 gets cancelled, 2 gets cancelled, again we will get same. If you pass 3 farads through both the solutions, 3 into 107.8 grams of silver will be deposited. The weight of copper deposited is 3 into 31.75 grams. So weight of silver and copper deposited is in the ratio of their equivalent weights or not? Always the weight of substance deposited we are getting in the ratio of their equivalent weights or not? Yes. 107.8 is nothing but equivalent weight of silver. 31.75 is nothing but equivalent weight of copper. That means W1 by W2 is nothing but what? E1 by E2 only. W1 by W2 is equal to E1 by E2 only. Or if you take volumes only, V1 by V2 is equal to VE1 by VE2, equivalent volume of first gas by equivalent volume of second gas only. Sometimes they may give one in weights and another one in volumes only. Okay. If it is given in weights, here we have to take equivalent weight only. Okay. For second component, we have to calculate volume of gas evolved. Okay. For first component, what is given? What is the weight of substance deposited is given. But for second, okay, for second component, what is the volume of gas evolved that we want to calculate? And in such case, we follow like this only. Okay. Here equivalent weight we will get, here equivalent volume only. This is Faraday's second law. For example, I am giving a question like this only. By passing certain quantity of electric current, by passing certain quantity of electric current, 18 grams of aluminum is deposited. By passing certain quantity of electric current, 18 grams of aluminum is deposited. Continuation. If we pass same quantity of electric current, what is the weight of copper deposited? If we pass same quantity of electric current, what is the weight of copper deposited? Ento student, what is the weight of copper deposited? How many equivalents of aluminum is deposited in here? 18 grams means how many equivalents? 2 equivalents. That means how many equivalents of copper will be deposited? 2 equivalents of copper. 2 equivalents of copper means 63.5 grams. Otherwise, you follow this one. W1 by W2, as we are passing same quantity of electric current, W1 by W2 is equal to E1 by E2. What is the weight of aluminum deposited given? 18. Weight of copper deposited we want to calculate. What is the equivalent weight of aluminum? 9 grams. What is the equivalent weight of copper? 31.75. So 2 only. 9 ones are 9 twos are. So 31.75 into 2, 63.5 grams. That is the weight of copper deposited. Otherwise, here 2 equivalents of aluminum is deposited, means how many equivalents of copper will be deposited? 2 equivalents of copper will be deposited. 2 equivalents of copper means one equivalent weight is 31.75, 2 equivalents means 63.5. Directly we can calculate like that also. Next, write and similar type of question. By passing certain quantity of electric current, 107.8 grams of silver is deposited. By passing certain quantity of electric current, 107.8 grams of silver is deposited. If we pass same quantity of electric current, what is the volume of hydrogen gas evolved? What is the volume of hydrogen gas evolved? 11.2 liters, right? Here what is the, how many equivalents of silver is deposited? One equivalent of silver is deposited. That means how many equivalents of hydrogen gas evolved? One equivalent of hydrogen gas is evolved. What is the equivalent volume of hydrogen? 11.2 liters. Okay. So the formula we follow like this, and W1 by V1, that is equal to E1 by equivalent volume, and equivalent volume we have to follow. Okay. So W1 by V2, that is equal to E1 by equivalent volume of second compound. So what is the weight of silver deposited? 107.8 by V2 we want to calculate. Volume of hydrogen gas evolved we want to calculate. What is the equivalent weight of silver, and 107.8. What is the equivalent volume of hydrogen gas? 11.2. Okay, under STP conditions, and so volume of hydrogen gas evolved under STP conditions is 11.2 liters. Okay, one equivalent of silver is deposited. So the volume of H2 gas evolved is also one equivalent, and so equivalent volume of H2 gas is 11.2 liters. Okay. Right, and similarly V1 by V2 is equal to VE1 by VE2 also we can calculate it. Okay, for example, by passing certain quantity of electric current, okay, by passing certain quantity of electric current, 5.6 liters of hydrogen gas is evolved. By passing certain quantity of electric current, 5.6 liters of hydrogen gas evolved. By passing certain quantity of electric current, 5.6 liters of hydrogen gas evolved. Okay, under STP conditions, only. Under STP conditions, if we pass same quantity of electric current, what is the volume of O2 gas evolved? What is the volume of O2 gas evolved under STP conditions? ఎంత వస్తుందండి? How many equivalents of hydrogen gas is evolved? One equivalent or half equivalent? Half equivalent of hydrogen gas is evolved. That means how many equivalents of O2 gas will be evolved? Half equivalent. What is the equivalent volume of O2? 5.6. Half of 5.6. 2.8 liters. Right. Okay. So V1 by V2 is equal to VE1 by VE2. The volume of hydrogen gas evolved is 5.6. V2 we want to calculate volume of O2 gas evolved. What is the equivalent volume of hydrogen gas? 11.2. What is the equivalent volume of O2 gas? 5.6. That means 2 times gets cancelled. So volume of O2 gas evolved is nothing but 5.6 by 2, that is 2.8 liters. Okay, here half equivalent of hydrogen gas is evolved, so the volume of oxygen gas evolved is also half equivalent volume, half of equivalent volume only. That means half of 5.6, so to get 2.8 liters. So directly we can calculate like this. So this is about Faraday's laws and Faraday's laws of electrolysis. Okay. Morning we discussed qualitatively and which products we will get. That is qualitative analysis we did. We discussed. Now quantitative analysis. How much amount of O2 gas is evolved? How much amount of H2 gas is evolved? So that quantitative analysis is done by Faraday's laws of electrolysis. Okay. Next one, resistance. Resistance or resistance. What is resistance? And that is inverse of conductance. Inverse of conductance is called resistance. Okay. So or it can be defined like this. And resistance is the obstruction to flow of current. Obstruction to flow of current is called resistance. obstruction to flow of current. Obstruction to flow of current is called resistance. Addanki and okay, right. Obstruction to flow of current is called resistance, or inverse of conductance. Inverse of conductance is called resistance. Simply inverse of conductance is called resistance. Conductance is nothing but our next topic, the ease with which a substance allows flow of current, that is called conductance. The tendency to allow passage of current, that is called conductance. Next one, right. It is observed that resistance is directly proportional to, experimentally it is observed that resistance is directly proportional to length of electrode and inversely proportional to area of cross section of an electrode. Resistance is directly proportional to what? Length of electrode and inversely proportional to area of cross section of an electrode. So here L is nothing but length of electrode. A is called area of cross section. Okay, area of cross section is related to what? Thickness, and that is related to what? Thickness. Area of cross section is related to what? Thickness of electrode. Experimentally it is observed that resistance is directly proportional to length of electrode and inversely proportional to area of cross section of electrode. For example, if you take long and okay, long and thin copper wire, and for example, if you take long and thin copper wire, then what about the resistance? And it possesses high resistance or low resistance. And okay, similarly we are taking short and thick copper wire. Out of these two, which one possesses high resistance? And first one or second one? And first one possesses high resistance. Okay, as the length of the electrode increases, resistance increases. As the area of cross section, thin copper wire we are taking, area of cross section is low, resistance is high. So therefore long and thin copper wire possess high resistance compared to short and thick copper wire. Right, long and thin copper wire has more resistance. Long and thin copper wire has more resistance compared to short and thick copper wire. Long and thin copper wire shows more resistance compared to short and thick copper wire. Okay, so now if you remove the proportionality, what we get? And we'll get some constant that is indicated with rho. So R is equal to rho into L by A. R is equal to rho into L by A, proportionality constant we are indicating as rho. So if you take, for example, L is equal to 1 centimeter or 1 meter under SI conditions, okay, and area 1 centimeter square or 1 meter square under SI conditions, okay, 1 centimeter and 1 centimeter square. Then what about volume? And if you take L value 1 centimeter and area 1 centimeter square, what we get? Volume 1 centimeter cube. 1 centimeter cube is nothing but what? 1 ml. 1 ml. Okay, we are taking length 1 unit and area also 1 unit, whether it may be centimeter or meter. Okay, whether it may be 1 centimeter square or 1 meter square. Volume 1 centimeter cube or 1 meter cube. Length we are taking 1 unit, area we are taking 1 unit, volume we are taking 1 unit. And so then these two are gets cancelled or not? Okay, 1 only. Okay, gets cancelled. So the resistance shown by that object is called what? Rho. And so how can you define rho? If you see, rho is nothing but resistance shown by 1 centimeter cube conductor. And resistance shown by 1 centimeter conductor or 1 ml electrolyte solution. 1 centimeter cube conductor or 1 ml electrolyte solution. That's why rho is called as specific resistance. Rho is called as specific resistance, or it is also called as resistivity. Why it is called specific resistance? And since it is nothing but resistance shown by 1 centimeter cube electronic conductor or 1 ml electrolyte solution andi. That's why it is also called as specific resistance andi. Okay, so rho is called as resistivity, rho is called as resistivity or specific resistance andi. Rho is called as resistivity or specific resistance. How can you define rho? It is the resistance shown by 1 centimeter cube electronic conductor or 1 ml electrolyte solution, right? It is the resistance shown by 1 centimeter cube electronic conductor or 1 ml electrolyte solution. 1 centimeter cube conductor or 1 ml electrolyte solution. That is under CGS units only. Okay. Next, what is the unit for rho? Unit for specific resistance or resistivity. Rho is equal to, what is the expression for rho only? R into A by L. R into A by L. So rho is equal to rho. What is the unit for R and resistance? Resistance unit is ohm. Ohm. This is centimeter square by centimeter. So therefore resistance unit, specific resistance unit is ohm centimeter. Ohm centimeter or ohm centimeter. So how can you determine resistance? And resistance we can calculate by using Wheatstone bridge. Wheatstone bridge that you may study in physics. Wheatstone bridge. By using Wheatstone bridge we can calculate resistance. Wheatstone bridge we can calculate resistance. So this is the concept of resistance and specific resistance. And specific resistance is nothing but resistance shown by 1 centimeter cube conductor or 1 ml electrolyte solution under CGS units. Okay. Now if you take SI units, what we will get? And ohm meter we will get. Ohm meter. Okay. Resistance unit is same only. Ohm meter we will get. 1 ohm meter is equal to 100 ohm centimeter. 1 meter is equal to 100 centimeters. So 1 ohm meter is equal to how many ohm centimeters will get? 100 ohm centimeters will get. Okay. This is the concept of resistance only. Next one, conductance. C. Conductance C. Conductance indicates what? It is nothing but inverse of resistance. Okay, right? Conductance, the ease with which a substance allows passage of current through it, that is called conductance. And right, the ease with which a substance allows the ease with which a substance allows passage of current through it is called conductance. The ease with which a substance allows passage of current through it is called conductance. If we have more obstruction to flow of current, smaller is the conductance. Okay, so C is nothing but reciprocal of resistance. C is equal to 1 by R. So from that we get C is equal to, what is the expression for R we have only? Rho into L by A. If you take inverse of R, what we get? 1 by rho into A by L. We get 1 by rho into A by L. So inverse of specific resistance is called specific conductance. 1 by rho is called as specific conductance or conductivity. Rho is called what? Resistivity. So 1 by rho is called what? Conductivity. That is indicated with Kn. So C is equal to K into A by L. Okay, again if you take same and L is equal to 1 centimeter, A is equal to 1 centimeter square, V is equal to 1 centimeter cube, then what we get? C is equal to K or not? A is equal to 1 unit, L is also 1 unit we are taking. A 1 unit, L also 1 unit, nothing but volume 1 unit we are taking, then C is equal to K. So how can you define K? Before that, K is also called as what? Conductivity or specific conductance, where K is called as conductivity or specific conductance. K is called as conductivity or specific conductance. How can you define K? K is defined like this. It is the conductance shown by, what? 1 centimeter cube conductor or 1 ml electrolyte solution. A is equal to 1 centimeter square and it is the conductance shown by what? 1 centimeter cube conductor or 1 ml electrolyte solution. Right? K is defined like this. K, it is the conductance shown by, 1 centimeter cube conductor, or 1 ml electrolyte solution, 1 ml electrolyte solution. Right, next one, unit for K and unit for K. K is nothing but 1 by rho. Unit for specific conductance, if you see 1 by rho, 1 by ohm centimeter will get. That means if you bring that to numerator, ohm inverse, centimeter inverse only. In SI units we get ohm inverse, meter inverse, ohm inverse, meter inverse. Or ohm inverse is also called as Simon and Simon centimeter inverse. In SI unit, Simon meter inverse will get. Simon meter inverse. Ohm inverse, centimeter inverse, 1 by ohm into centimeter. So we get ohm inverse, centimeter inverse, ohm inverse. Okay. Or Simon centimeter inverse. That is the unit for K. So this is the concept of conductance and resistance. Next one, cell constant. A small concept, cell constant X. Cell constant X. Cell constant X. So we have a solution and we want to measure its conductance. To measure its conductance, what we have to use? We have to take conductivity cell. We have to take what? Conductivity cell. This conductivity cell possesses 2 platinum electrodes or 2 platinized platinum electrodes. Okay, so that we have to connect to conductivity meter. This is called what? Conductivity cell. Okay, conductometric titrations. While we are doing conductometric titrations, we use conductivity cell or not? Yes, we use conductivity cell. It consists of 2 platinum electrodes. This is conductivity meter. Conductivity meter. Here we get some reading, that is conductance. Okay, conductivity values we can measure. Conductivity values. Okay. So by using conductivity cell, we can give contact between meter and solution. The contact between meter and solution can be done by what? Conductivity cell. Okay. Now here if you see in conductivity cell we have 2 platinum electrodes. The length between 2 platinum electrodes is fixed or not? Yes, the length between 2 platinum electrodes is fixed, and the area present between 2 platinum electrodes is also fixed. So for a given conductivity cell, L and A are constant. Length between 2 platinum electrodes and area present between 2 platinum electrodes is fixed. Okay. So L and A are fixed, then what about L by A is also fixed. L by A is also a constant for a given conductivity cell. That L by A is called as cell constant. That L by A is called as cell constant, right? For a given conductivity cell, for a given conductivity cell, for a given conductivity cell, L and A are constant. L means what? Length between two platinum electrodes. This is L and okay, this is L, the length between two electrodes, and that is area. Under the area is nothing, A is nothing but the area present between two platinum electrodes. For a given conductivity cell, L and A are constant, so L by A is also constant. So L by A is also constant, which is called as, so L by A is also constant, which is called as cell constant, which is called as cell constant. That is represented by what? X. And so what is the expression for cell constant? And L by A. The expression for cell constant is L by A. On each conductivity cell, that value is written, and that value will be displayed on each conductivity cell. What is the L by A value for a given conductivity cell? That value is written on each conductivity cell, around 1. Its value is around 1, that is written on the conductivity cell. What is the unit for conductivity cell constant? And L by A, centimeter inverse, centimeter by centimeter square. In CGS units we will get centimeter inverse. If you go to SI units, we will get meter inverse. X is equal to centimeter inverse. That is the unit for cell constant. So with respect to cell constant, if you take the expressions for resistance and conductance, what is the expression for resistance? And R is equal to rho into L by A. What about L by A? Is called X. So therefore R is equal to rho into X. And this is the expression for resistance with respect to cell constant. Next, inverse of resistance is called conductance. So C is equal to 1 by rho into X. We will get C is equal to 1 by rho into X. So 1 by rho is called what? K. K by X. 1 by rho is called K. So this is the expression for what? Conductivity and with respect to cell constant, where K is called what? Specific conductance or conductivity. So the formula for specific conductance is equal to cell constant into conductance. And what is the formula for specific conductance? Cell constant into conductance. C is conductance. And okay, C simply in the place of L by A we have written X, and R is equal to rho into X. Inverse of resistance is called conductance. So 1 by rho into X. 1 by rho is called specific conductance. So the expression for specific conductance is X into C. And okay. Next, and how to calculate resistivity? If you see resistance, and resistance, okay, or resistivity, if you see R is equal to what we get? And X by K kada, 1 by rho, ante kadandi. Rho is nothing but 1 by K. So R is equal to X by K. So resistance we can calculate experimentally by taking a solution whose conductivity is already known. And how generally we can calculate resistance? If you see, resistance is calculated by taking a solution whose conductivity value is already known. So for that purpose we use KCL solution, right? Resistance is calculated by taking a solution whose conductivity is, by taking a solution whose conductivity is already known. Resistance is calculated by taking a solution whose conductivity is already known. Okay, so for this purpose we use 0.01 m KCl solution. 0.01 m KCl solution whose conductivity value is around 1412 microsiemens per centimeter. Whose conductivity value is 1412 microsiemens per centimeter. Okay, and Simon per centimeter kadandi. Microsiemens means into 10 power minus 6 we will get, into 10 power minus 6 andi. 1412 into 10 power minus 6 microsiemens per centimeter andi. So we use KCl. It is a stable compound. KCl is a stable compound. That's why we use KCl andi. Okay, whose conductivity value is already known. For calibration purpose also, what we use and conductivity meter calibration purpose also we use KCl only. Since its conductivity value is already known to us, we use generally 0.01 m KCl and at different concentrations we get different value and generally we use 0.01 KCl whose conductivity value is 1412. Okay, Nandi? So we discuss the cell constant for a given conductivity cell. The length between two electrodes and the area between two platinum electrodes is constant. So L by A is fixed. So that is called cell constant. The unit is centimeter inverse. So with respect to cell constant, these are the expressions for resistance and conductance. Okay, so generally how we can calculate resistance and by taking a solution whose conductivity value is known to us. For that what we use 0.01 m KCl we can use whose K value is 1412. Okay. Next one, molar conductance and equivalent conductance. Next one, molar conductance. Mu, or it may be indicated as lambda m. Molar conductance is indicated as lambda m. So the name itself indicates it is the conductance of a given solution. It is the conductance of solution containing how much amount of substance? 1 mole of substance. Okay, whatever may be the volume of solution, it has to contain how much electrolyte? 1 mole of electrolyte. Then the conductance shown is called molar conductance. Whatever may be the volume of solution, if the given solution contains 1 mole of electrolyte, then its conductance is called molar conductance. Okay, for example, I am taking 1 liter solution. In 1 liter solution, 1 mole of NaOH is present. 1 mole of NaOH is present, for example. What is its conductance? Its conductance is called as what? Molar conductance. Since this 1 liter solution contains how much amount of electrolyte? 1 mole of electrolytes. So its conductance is called molar conductance. Now for example, I am taking 2 liter solution. That also contains 1 mole of NaOH only. 2 liter solution that contains how much NaOH? 1 mole of electrolyte. What is its conductance called? Molar conductance. The conductance shown by this solution is called molar conductance. The conductance shown by this solution also called molar conductance. So in general, for example, we have VML solution. For example, we have VML solution containing 1 mole of electrolyte. In general, we are taking VML of solution containing 1 mole of electrolyte. What about the conductance shown by this solution is called molar conductance. So whatever may be the volume of solution. Okay, if it contains 1 mole of electrolyte, it is called molar conductance. If it is over, then write the definition. First you write this. tomorrow I will start an important concept, Kohlraasch's law, and important for all competitive exams. Okay. How can you define molar conductance? And it is the conductance of solution containing 1 mole of electrolyte. It is the conductance of solution. It is the conductance of solution containing 1 mole of electrolyte. It is the conductance of solution containing 1 mole of electrolyte. Okay. So whatever may be the volume of solution, if 40 grams of NaOH is present in that, its conductance is called molar conductance. Okay. We know the conductance shown by 1 ml of solution. Okay. Conductance shown by 1 ml of solution is called as what? Conductance shown by 1 ml of electrolyte solution is called what? Specific conductance or conductivity. Specific conductance or conductivity. So conductance is nothing but what? K. If you take 1 mole of electrolyte solution, the conductance shown by that 1 ml of electrolyte solution is called what? Specific conductance K or conductivity. Now if you take VML of solution, okay, here how much amount of solution we are taking? VML of solution. VML of solution we are taking containing how much electrolyte? This is the main condition. It has to contain how much amount of electrolyte? 1 mole of electrolyte. Now we are taking VML of solution containing 1 mole of electrolyte. Its conductance is called what? Molar conductance. Its conductance is called molar conductance. Then what is the formula for molar conductance? We will get it. Okay, lambda m r mu. What is the formula for molar conductance? We will get it. For 1 ml conductance is K. For 2 ml conductance is 2K. For VML conductance what we get? Vk we will get. Okay, right? So therefore the formula for molar conductance is nothing but K into V in ml and K into V in ml. But the condition is this VML of solution contains how much electrolyte? 1 mole of electrolyte. That is the condition. Then only it is called molar conductance. So the formula for molar conductance is K into V in ml. Okay, or we can write like this also only. If you take the expression for concentration in molarity, Cm, I am writing concentration in molarity. What is the formula? Number of moles by volume in ml into 1000. What is the formula for concentration in molarity? Number of moles by volume in ml into 1000. Okay. If you take volume in ml, if you take the expression for volume in ml, so volume in ml is equal to what is the number of moles of electrolyte we are taking? 1 mole of electrolyte. So N is 1. So what we get? 1000 by concentration in molarity. So since N value is 1, so volume in ml we can write as what? 1000 by concentration in molarity. So the formula for molar conductance is, this is the formula, K in ohm inverse centimeter inverse into CGS units only, K in ohm inverse centimeter inverse into volume in ml. Volume in ml we can write as 1000 by concentration in molarity. Concentration in molarity. The unit we get like this only. This is ohm inverse centimeter inverse. Okay. Must you write only. Mu is equal to K into 1000 by concentration in molarity. Okay, CGS units we are taking K in ohm inverse centimeter inverse. And now K unit is ohm inverse centimeter inverse, volume unit ml. ml means we can write as centimeter cube or not? Centimeter cube. Okay, and we are calculating for 1 mole of electrolyte, so per mole. So ohm inverse centimeter square per mole we will get it. Ohm inverse centimeter square per mole. That is the unit for molar conductance. What is the unit for molar conductance? Ohm inverse centimeter square per mole. Ohm inverse centimeter square per mole. This is the unit for molar conductance. Okay, Nandi. So what is the unit for K in CGS units? That is ohm inverse centimeter inverse. What is the unit for volume, Andi? ml. ml means we can write as centimeter cube. And this VML solution contains how much amount of electrolyte? 1 mole of electrolyte. So we are calculating for 1 mole of electrolyte. So ohm inverse centimeter square per mole we will get it. So if you convert into ohm inverse meter inverse, and we will get like this, and okay, that conversion I am not giving, just you remember that K into ohm inverse meter inverse by 1000 into concentration in molarity. If you convert this centimeter inverse to meter inverse, we will get like this, and here we will get ohm inverse meter square per mole. This is another expression we have. In CSIR, they are giving with respect to ohm centimeters, with respect to meters, they are giving sometimes with respect to decimeter also. In CSIR, we are getting with respect to decimeter also. In terms of decimeter, we have this equation. In terms of centimeters, we will get 1000 in the numerator. In terms of meters, 1000 we will get in the denominator. In terms of decimeter, we cannot get 1000. Okay, just you remember ohm inverse decimeter inverse by concentration in molarity, then we get in ohm inverse decimeter square per mole. So unit conversions we have to do and not required, just remember centimeters to meters, meters to decimeters, that unit conversions we have to use. Finally we get like this, and these are the various expressions for molar conductance we have. So just give me 5 minutes, and I will complete equivalent conductance also. Just 5 minutes. Similarly we can write, and similarly we can write. That's why. Okay. So molar conductance is nothing but the conductance shown by VML of solution containing 1 mole of electrolyte. That is called molar conductance. This is the formula. So from concentration in molarity, V in ml we can write as 1000 by concentration in molarity. This is in CGS units, and if you convert into meters, we will get like this. If you convert into decimeters, we will get like this. Next one, and equivalent conductance. A small difference we have, and equivalent conductance lambda. So just by this symbol, don't differentiate between equivalent and molar conductance. Based on units, you can differentiate easily, and okay, here per mole we will get, there per gram equivalent we will get. So mostly you follow what? To differentiate molar conductance and equivalent conductance, you follow unit, and to differentiate molar conductance and equivalent conductance, you follow unit. Since in most of the cases they have given same symbol for molar conductance and equivalent conductance, lambda only. But the difference is what? Unit is different. This is for 1 mole of electrolyte, that is for 1 gram equivalent of electrolyte. Okay. So whatever may be the amount of substance, the solution has to contain how much, and how much amount of electrolyte, and 1 gram equivalent of electrolyte. The solution contains, first you listen, I will give some time. Okay, if the solution contains 1 gram equivalent of electrolyte, then the conductance is called what? Equivalent conductance. So in general, if VML of solution contains 1 gram equivalent of electrolyte, then its conductance is called equivalent conductance. So same only. If 1 ml of solution, if you take, its conductance is called specific conductance. Now what is the solution volume we are taking? VML solution that contains how much amount of electrolyte? 1 gram equivalent of electrolyte. Then its conductance is called what? Specific conductance. Same formula, but the difference is what? Here VML solution contains 1 gram equivalent of electrolyte. Previously VML solution contains 1 mole of electrolyte. Okay, so now I am taking concentration in normality, and number of gram equivalents by number of gram equivalents, and number of gram equivalents by volume in ml into 1000. How many gram equivalents we are taking? 1 gram equivalent. So n value 1. So volume in ml is nothing but what we get? 1000 by concentration in normality. So that is difference. So we get concentration in normality. What is the unit we will get? Per mole or per gram equivalent? Per gram equivalent. Ohm inverse centimeter square per gram equivalent. As we are taking 1 gram equivalent of electrolyte. This is about equivalent conductance. Only small difference. How much amount of electrolyte we are taking? 1 gram equivalent of electrolyte. Whatever may be the volume of solution, if it contains 1 gram equivalent of electrolyte, then its conductance is called equivalent conductance. So concentration in normality formula is number of gram equivalents by volume in ml into 1000. As we are taking n value 1, so volume in ml we can write 1000 by Cn. Just in the place of Cm we get Cn. Normality we will get. In the place of molarity we get normality. Write down. So tomorrow we will see the relation between molar conductance and equivalent conductance and effect of dilution on these conductance, and then we will go to Kohlrausch law. As tomorrow last day, okay, I will take 9:30 to 1, okay. 9:30 to 1 p.m. If any changes, okay, I will post in our group, okay. If possible, we will discuss summary on electrochemistry, okay. Otherwise, we will discuss next week. How can you define equivalent conductance? It is the conductance shown by 1 gram equivalent of solution. It is the conductance shown by 1 gram equivalent of solution, or it is the conductance of solution containing 1 gram equivalent of electrolyte. It is the conductance of solution containing 1 gram equivalent of electrolyte. So tomorrow morning timings 9:30 to 1 p.m. Okay, possible 1, otherwise I will complete up to 12:30. Okay, right. Okay, right, thank you.